In this video, we're going to go over the multiplicity of a proton NMR signal. And the multiplicity is basically the number of peaks that we see in the signal. So on the left, here we have just one signal, and there's no splitting pattern, so this is just a singlet. Here it splits into two parts. This is a doublet, and below it you can see the intensity ratio of those two peaks. It's a 1-to-1 ratio. Next, we have a triplet, which appears as three signals. It's really one signal, but split into three. And the intensity ratio for that is 1-to-1. If it splits into four parts, you have a quartet. And for 5 is a quintet, 6 is a sextet, and 7 is a septet. Sometimes, if you have more than 4, like if you have 5 or more, you could just call it a multiplet sometimes, which might be easier to do it that way. Now let's focus on the intensity ratios that we see for like a quartet or a quintet. You don't have to memorize these numbers because there's a very simple way in which you can find these numbers for the different types of signals that we can have. Now there's something called Pascal's Triangle, which I'm sure you heard some point in either in high school or college when you took algebra or a pre-cal. The first number is a 1. And then the next number, the next row will have two 1s. So this is just the intensity ratio for a singlet, and this is the intensity ratio for a doublet. Next, add the two numbers. 1 plus 1 is 2. Now you're always going to have a 1 on the left side and on the right side. So this is the intensity ratio for a triplet. Now if we add 1 plus 2, that gives us 3. And if we add 2 plus 1, it also gives us 3. And put a 1 at the edges of the triangle. So now we have the intensity ratio for a quartet. 3 plus 3 is 6, 1 plus 3 is 4, 3 plus 1 is 4, and now we have the intensity ratio for a quintet. Now 4 plus 6 is 10, 6 plus 4 is 10, 1 plus 4 is 5, so this gives us the intensity ratio for a sextet. 10 plus 10 is 20, 10 plus 5 is 15, 1 plus 5 is 6, and so now we have the intensity ratio for a septet. It's amazing how some of the things that you've learned in math now comes into play with things like this, like NMR. Who would have known that Pascal's Triangle would be related to it? So that's a quick and simple way in which you could find the intensity ratios for the splitting patterns that you'll see in an NMR spectrum. Now let's work on an example problem. Let's use ethyl bromide as an example. And what we're going to do here is we're going to draw a rough sketch of the proton NMR spectrum for this molecule. So right now, we need to determine how many signals we would get in this molecule. Notice that there's two different types of protons. The 3 protons in the methyl group are equivalent to each other, so they will show up as one signal, which we can call signal A, and the 2 protons in the CH2 group will show up as one signal. Now, what is the splitting pattern for the CH3 protons, or protons A? What is the splitting pattern for those protons? What would you say? Would you say it's a singlet, doublet, triplet, quartet? Now there's something called the N+1 rule. The N+1 rule allows us to determine what type of splitting pattern we're going to get. So if we're analyzing proton A, you need to look at the adjacent protons. In this case, proton B. So N is the number of protons on the adjacent carbon. So we have 2 protons plus 1, that's going to be 3. And 3 corresponds to the signal of a triplet. Now let's analyze proton B. So looking at the adjacent carbon, there are 3 protons on it. So N is 3. Using the N+1 rule, we have 3 plus 1, which is 4. And so we're going to get a quartet with the intensity ratio 1:3:3:1. So that's how you could determine what type of splitting pattern you have using the N+1 rule. Now, in order to draw the graph, we need to determine the location of these signals. A CH2 group attached to a Br, that's going to have a chemical shift somewhere between 3 to 4. And a methyl group is usually around 1-ish, but because of the presence of this electron withdrawn group, it turns out that an ethyl bromide is going to be shifted upfield, or not upfield, but shifted downfield to about 1.6. So let's draw the signal for the methyl group. So around 1.6, we're going to have a triplet. And so we're going to get something that looks like that. Let me use a different color. My drawing is not perfect, but you get the point. Now, for the CH2 group, those protons will show a signal, let's say about 3.5. And so we could show the quartet like that. And so that's how you could use the N+1 rule to either draw an NMR spectrum or even identify the signals on a graph to determine which molecule corresponds to it. Now, the only other thing we need to mention is the integration. Notice that we have 3 protons for signal A. And this is for the triplet, this is for the quartet. To indicate the integration, we could say that the triplet corresponds to 3H, and the quartet signal corresponds to 2H. Now, what you need to understand with regard to the integration is that the number of protons, the ratio between the number of protons of the different signals correspond to the ratio of the area under the curve in those signals. So just keep that in mind. Typically, the signal will, with the higher number of protons, usually corresponds to a signal with a greater height, so to speak. Because the greater the area under the curve is, the greater the height of the signal. So we expect that this signal will be taller than this one. But technically, the ratio of the protons corresponds to the ratio of the area under the curve for each signal. Now let's consider this example. So we have the molecule 1-nitropropane, and there's 3 different types of protons on it. Go ahead and match every proton or every different type of proton with the signals that we see here in the H NMR spectrum shown below. Feel free to pause the video and work out this example. So the first thing we should do is identify the different types of protons. And we can clearly see that there's 3 of them: proton A, B, and C. Now let's determine the multiplicity of each proton that we have in this molecule. So let's look at the CH3 first. Proton A is adjacent to 2 other protons. So using the N+1 rule, we have 2 + 1, which is 3. Now proton C is adjacent to 2 protons. So using the same N+1 rule, 2 + 1 is 3. Now what about the one in the middle? Because right now, we see that we have 2 triplets, which corresponds to these 2 signals. The one in the middle appears to be 6, or a sextet. And if we look at the adjacent protons, we have 3 on the left, 2 on the right. So 3 + 2 is 5. Using the N+1 rule, 5 + 1 is 6. Now, this is basically a simplified version of the N+1 rule when you're looking at 2 different types of protons. Now, it's important to understand that this is not the most accurate way to get the multiplicity for this type of proton when there's 2 different types of protons adjacent to it. In most cases, it will suffice, as you can see that proton B has to correspond to this one, but it's not the best way. It's not the most accurate way of doing it. What we should do is this. So analyzing proton B, we need to look at the adjacent protons. So proton A will split B using the N+1 rule, so 3 plus 1 is 4. It's going to split it into a quartet. So we have 4. Next, we need to look at the other adjacent protons, that is proton C, and it's going to split protons B into a triplet because 2 plus 1 is 3. So what you're going to have is 4 times 3 or 3 times 4. So really, we should have 12 peaks for this signal. However, some of the peaks overlap, and so it looks like as if it's 6, but it's really not. It's 4 times 3. So that's how you're supposed to use the N+1 rule when you're dealing with adjacent protons that are not equivalent to each other. So this could mean we have a quartet of triplets, or it could be 3 times 4. It can mean that we have a triplet of quartets. I won't go into the specifics of that because that falls in the realm of complex splitting. Just know that when you're dealing with a proton in the middle, if the adjacent protons are not equivalent, you need to multiply the effect that they have using the N+1 rule. So this is 3 plus 1 is 4. This is 2 plus 1 is 3. So you do 4 times 3 and you should get 12. So instead of calling this a sextet, which is what it appears to be here, it's best to call it just a multiplet. And so far we have a triplet, multiplet, and a triplet. So this has to correspond to proton B. Now, which one is proton A and which one is proton C? Proton C is next to a very powerful electron withdrawing group, the NO2 group. And so it's going to cause it to be downfield. So it's going to have a high chemical shift. So therefore, this will be proton C between 4 and 5. Proton A is upfield. It's very far away from the electron withdrawing group. So this will be proton A, which is a triplet. And so this corresponds to 2H. Let's see if I can put it up here. And this corresponds also to a 2H. And this corresponds to a 3H. So that's how you could use multiplicity to basically match up the protons with the signals that we see in the corresponding H NMR spectrum. Now, for those of you who may want to know what a quartet of triplets look like and a triplet of quartets, here's how you can draw it. So let's start with a quartet of triplets. So what this means is that we have 4 triplets. So here's the first triplet with a 1-to-1 ratio, and here's the second one. And then here is the third triplet, which is smaller, and then the fourth triplet. So we have 4 triplets, and the ratio of the areas of those triplets will be in a 1-to-3 to 3-to-1 ratio, which corresponds to a quartet. So that is a quartet of triplets. That's how it looks like. Now let's talk about a triplet of quartets. So this means we have 3 quartets. So here is the first quartet. Let me draw a straighter line. And here is the second quartet, which is smaller than the one in the middle. And here's the last one. So those are the 3 quartets. And each quartet has a ratio, as you can see, of 1-to-3 to 1 for their intensities. However, for each of the 3 quartets, the ratio of their areas is going to be 1-to-2 to 1, which corresponds to a triplet. So that's a triplet of quartets, or 3 quartets. Now let's talk about why we get the intensity ratios that we get for a doublet, a triplet, and a quartet. So let's say we have this situation. Let's say we have proton A and proton B, and we're analyzing the signal for proton A, and there's only one adjacent proton to proton A, as we can see here. So using the N+1 rule, this will give us a doublet. And so I'm going to draw it like this. So let's see why the intensity ratio is 1:1 for a doublet. Now it has to do with the way the protons are aligned with the magnetic field. Every proton has its own magnetic moment. It has its own magnetic field, which can be aligned with the external magnetic field of the NMR spectrometer, or it can be aligned against it. So let's say this is the applied magnetic field. Proton B can have a magnetic field that is aligned with the applied magnetic field, or it can have a magnetic field that's aligned against it. Now, if it's aligned with the magnetic field, the net effect on proton A will be a stronger magnetic field because those two lines will add up. And so this particular peak will appear downfield. It's going to have a higher frequency due to the stronger net magnetic field. Now, this peak appears with a lower frequency. It appears slightly upfield because the net magnetic field is weaker. The applied magnetic field and the magnetic field of the adjacent proton, they go against each other. And so the net magnetic field is weaker, and that's why it appears at a slightly lower frequency. So because the magnetic field of proton B can have two possibilities, either it can be aligned with the magnetic field, the external magnetic field, or it can be aligned against it, and these two possibilities are roughly equal. That's why the intensity is in the 1:1 ratio. But now let's look at another example. So let's see if we have a triplet, why the intensity ratio is 1:1. So we need another proton here. So in this case, proton A is being split by two protons, two adjacent protons. So 2 + 1 will give us 3. We're going to get the triplet. So let's draw a picture of the triplet to begin with. So it's going to look something like this. So as we can see, there's 3 peaks in this signal. And let's draw the direction of the external applied magnetic field. So we have 2 protons. So we're going to draw an arrow for each of those protons. So for this particular peak, the protons have to be aligned with the magnetic field because it's furthest downfield. It's at the highest frequency, which means the net magnetic field has to be the strongest. So both protons are in the same direction with that field. Now to get the one on the right, that peak corresponds to a low frequency. So that's when the 2 protons will be against the applied magnetic field, thus giving us the weakest net magnetic field that's acting on this proton. So we have 2 fields that are aligned with the magnetic field and 2 that are aligned against it. Now we could have one with and one against the magnetic field, or the first one could be against it and the second one could be with it. So thus we have our 1:1 ratio. So this is when both protons are aligned with the magnetic field, and this is when both protons, that is these 2, are aligned against the magnetic field. And in the middle, you can have one that's aligned with it or one that's aligned against it. And so that's why we can see why we have a 1:2:1 ratio. Now let's consider the last case. That is when we are going to get a quartet. So we're going to need 3 adjacent protons. And the intensity ratio is going to be 1:3:3:1. So we're going to get something that looks like this. So for the first one, all three of these protons will be aligned with the magnetic field. I'm going to draw it here. For the last one, where it's upfield, all three protons can have the magnetic field against the external magnetic field. Now for this one here, we can have two that are aligned with the magnetic field, and one will be against it. So it can be up, up, down. It can be up, down, up, or it could be down, up, up. So there's three possibilities in which two of the three magnetic fields will be aligned with the magnetic field. Now for this one, we're going to have one that is aligned with the magnetic field and two against it. So it can be up, down, down, or it could be down, up, down, or down, down, and then up. So in this case, we have all three that's aligned with the magnetic field. Here we have two aligned with the magnetic field. And for this one, there's only one that's aligned with the magnetic field. And for the last one, there's none. And you can see that we have a 1 to 3 to 3 to 1 ratio. And so now you know why we get the intensities that we see in the NMR spectrum. And this is the basic idea behind spin-spin splitting. It has to do with the way that the adjacent protons align with the external magnetic field, thus affecting the proton that we're analyzing.